Ya estamos, ya. Buenas tardes, entonces, bienvenidos a un seminario de Ingeniería Civil Transporte, del programa de Magíster en Transporte, y bueno, también del doctorado en Ingeniería Civil y doctorado en Sistema de Ingeniería, todos los doctorados. Es un placer para nosotros. Tenemos un invitado, Hajime Watanabe.
Yes.
I'm not sure I'm pronouncing your name correctly, so please forgive me. La presentación va a ser en inglés. Hajime hizo el doctorado en la Universidad de Kumamoto en Japón y ahora es un postdoc en la Universidad de Tokio. Terminado su doctorado. Él es originalmente de pregrado de Ingeniería Civil y se ha dedicado a la modelación de lecciones discretas con aplicación a lección residencial principalmente, a la parte egonométrica, eso ya, que es una parte que le tengo mucho cariño porque es a la que me dedico yo. ¿Ya? Entonces vamos a dejar más preámbulo, digamos, alguna cosa. Más preámbulo voy a dejar a Jimé que esté presente, y bueno, la presentación va a ser en inglés. En caso que alguien tenga alguna pregunta y la quiera hacer en español, no hay problema, y la podemos traducir acá. Ya tenemos gente, tenemos algunas tres personas, bueno, contando a Gabriel también, 4 personas en la sala y algunas personas en YouTube. Ya, así que adelante, Jimé.
Thank you. Thank you for introducing Professor. Thank you for coming today. And my name is Hajime Watanabe from the University of Tokyo, Japan. Today I'm going to talk about my research. And first of all, I'd like to introduce myself. So my research interest is activity probability behavior analysis using discrete choice modeling and causal inference. And also my research interest is disaster recovery, because there are so many earthquakes in Japan, actually. Yes. So I got my PhD at the University of Kumamoto, and then I moved to Tokyo, and I started to work as a postdoctoral researcher. So Kumamoto is a relatively suburban city, rural city, and moved to Tokyo is very mega city. So I was very confused to live in such a big city. And every year, like me, so many young people move to Tokyo from suburban cities like Kumamoto. So it is a very serious social issue, and it is one of my research background. And also, another serious issue is the population has decreasing over the years due to declining birth rate and aging population in Japan. So, yeah, most of us live in some specific area like Tokyo, Osaka, Fukuoka. So public transportation in such area are well developed and easy to use. But otherwise, in public transportation in other areas are very poor, and less people use public transportation in other areas. But in Japan, due to the declining birth rate and aging population in Japan, public transportation services in suburbs is not profitable, and thus it's very hard to maintain. It has been shrinking. So the Japanese government recommend people to use public transportation, not to drive their own car. So I would say a solution can be a compact city and transit-oriented development. And the benefits have been discussed over the years in our field. So the benefits are expected, but not guaranteed. So we need to check whether the causal effect of relocation or the intervention, probability behavior, is effective or not to address such a social issue in Japan. So let me talk about causal inference research in our field. And I introduced a research paper written by not transportation researcher. They research in with a medical or health background. And they reviewed papers, existing papers at that time, and argued that transportation researchers should use experimental study designs. But I would say it is the experimental study design very impractical in reality. This is because experiments randomly assign people to treatment and control groups. So for example, assuming treatment group as living in urban area and control group as living in a rural area. In this case, researchers, analysts should people assigned to treatment and control group randomly. These are experimental study design transportation research field. But in reality, it's very difficult to randomly assign their location, destination location, due to ethical reasons or financial reasons. Yeah, so many reasons. So instead, we should consider the alternatives. It is called quasi-experimental study design. In other words, observational study. It uses observational data and estimate the causal inference, causal effects statistically using some models and some techniques. But the weakness of this quasi-experimental study design is it lacks the element of randomly assignment to treatment or control groups. So it needs to address the potential non-random assignment because people choose their destination locations by themselves. So it needs to address the potential non-random assignment. And in this context of destination self-selection, it is called the endogeneity problem due to destination self-selection. Because people self-select their destination locations, it causes the endogeneity issues. So another background is existing method, available method in our research field. So in general, if analysis perfectly observe attitudinal and other important factors which cause endogeneity issues, they can use many existing methods in my understanding. And in this case, there can be no room for endogeneity problem. But in practice, it is very difficult to capture such attitudinal variables perfectly. So otherwise, we should consider the following three major methods. For example, instrumental variable approach and the multiple indicator solutions. These two methods are very famous and useful. But in this presentation, I focus on the third one. This is called the sample selection modeling approach. It is originally proposed by Ekman. He's an economist and he got a Nobel Prize in 2000. And this approach is addressing endogeneity issues by assuming treatment and control group assignment. So in this framework, so in short, the sample selection modeling approach addresses the endogeneity issues in this experimental study design framework. And the strength of this approach is it doesn't require instrumental variables and other indicators. And also, it doesn't need solo observation of attitudinal variables, like instrumental variable and MIS approaches. But the weakness of this approach is it must assume treatment and control groups because it addresses endogeneity in this framework, so it must assume treatment and control group. And actually, it is very restrictive. So, best studies employ this sample selection modeling approach. So, the research challenge is existing available sample selection models are too simple for travel behavior analysis because it assumes two groups, and the differences between the two groups is defined as causal effect on a travel behavior. So my research objective is to propose a new and flexible sample selection model to identify a causal effect of interventions or relocations on travel behavior. Okay, next, I would like to explain a sample selection model. So let me explain first the Rubin causal model framework. It is employed in the medical research or as a research field. So an ideal, this individual, we want to know the individual causal effect. For example, my travel behavior in Santiago and my travel behavior in Tokyo. The difference means the causal effect of the virtual environment in Santiago and Tokyo on my travel behavior. But in reality, both travel behavior are not observed at the same time. So instead, we will identify a population level causal effect. So we cannot identify the individual level causal effect. So instead, we identify a population level causal effect. So the differences in the travel behavior between the two groups. Yes. So people are randomly assigned to treatment and control groups. And as I said, one of the potential outcomes is always missing, since it is impossible to see both potential outcomes at the same time. So if an individual is treatment group, only Y1. This is usually continuous travel behavior outcomes is observed, and the other is missing. And likewise, if an individual is assigned to control group, only Y0 is observed. And the differences of the average of travel behavior outcomes is defined as the population level causal effect. So it is Rubin causal model framework for causal inference. But there's potential issues. For example, if rich people live in an urban area, treatment group, and the other people live in suburban cities in control groups, and such a financial status affects the travel behavior, the differences between two groups is not causal effect of our interest. So we need to control the social demographic variables using such a statistical modeling approach. So X is the explanatory variable, including social demographic variables, and beta is the corresponding parameters. And we consider such effect of social demographic attributes in X beta, and by doing so, we control such a social demographic variables. And the population level causal effect, ATE, is defined as follows. However, this Rubin causal model framework is assumed that people must be randomly assigned to treatment and control group conditional on the social demographic variables. So otherwise, estimated corresponding parameters can be estimated biasly. So this is called the residential selection problem. And for example, if an individual chooses their residential locations while thinking their future travel behavior and their family, thinking about their financial status or whatever, but they choose their residential locations by themselves. So in this case, travel behavior outcomes are non-randomly missing due to subjective and accident factors. And it is very hard to observe what they think when they choose their essential locations. And such variables are rarely observed. So we cannot include in such information, such a subjective actionary information in these explorative variables. And that's why in most of cases, people are not randomly assigned to treatment and control groups. By doing so, in this case, behavior outcomes are missing at not random. So sample selection modeling approach directly address these issues. For example, this modeling approach assumes licenser choice model, which is a binary probability model. And if the latent utility Zi star is greater than 0, the licenser choice, the variable is 1, and otherwise the variable is 0. And if Z is 0, 1, the travel behavior model is Y1, and otherwise Y0. So the travel behavior models are switched by licenser choice results. It is called binary endogenous switching, because travel behavior modeling is switched by the licenser choice results. And as I said, people can be non-randomly assigned to treatment and control groups. So the sigma captures the non-randomness of the assignment to treatment and control groups. So epsilon is the error term of these latent utilities, and UI, U1 and U0, the error term of the travel behavior models, and the sigma captures the error correlations. So by doing so, the error structures describe the non-random assignment to treatment and control groups. So by doing so, the parameters are not biased in such case. But as I said, it is too simple to analyze travel behavior outcomes because only one treatment group and only one control group is, and the difference, that's all in this approach. So it is too simple and it's not insightful enough. So I propose a more extended sample selection models while maintaining the advantage of this approach. For example, it employs a multinomial endogenous switching. So travel behavior model is switched based on the multinomial choice, or the essential choice, location choice. And we assume multiple control groups. Unlike the existing sample selection models, it assumes only one control group. But our proposal model assumes multiple control groups. And the error structure is shown here. And the essential choice, the error correlations are captured by sigma, as with the existing sample selection models. This is the model structure I proposed. And as with existing sample selection models, the observed missing matrix are shown here in the same manner. For example, an individual is assigned to treatment group, only Y1 is observed, and other travel behavior outcomes are missing. Yeah. For example, if an individual is assigned to control group 2, only Y3 is observed, like something like that. And using the data derived from the people in a treatment group, we estimate the parameter beta 1, and likewise, we estimate the beta 2 and beta j, and we calculate the expectation of the travel behavior outcomes, and we calculate the average. So, and the difference is defined as the causal effect between the two groups, treatment and control group 1. And the difference between here and here is defined as the causal effect between treatment group and control group 2. Yeah, something like that. So it is more insightful compared to the existing sample selection models because we can identify the causal effect multiply, and we can capture the effect of the endogeneity in each location, essential locations, not only one control group. Okay, finally, let me explain the likelihood of this model. And as I said, we employ a multinomial endogenous switching. And if an individual choose to live in a location J, only Yi J is observed, and other behavior outcomes are missing. So in this case, it is the overall model structures, and missing tribal behavior outcomes are marginalized, and then only here it's observed. Essential location choice, the latent utility of the essential location choice models, and tribal behavior outcomes. So the likelihood is the joint probability functions of the probability of choosing location, living location J, and probability behavior outcome. And theta is model parameter vector, and it is the likelihood of the proposed model. Okay, so as I shown in the previous slide, it is very huge and complex error structure. So I employ a Bayesian estimation because the usual maximum likelihood cannot apply in this case. So I briefly explain the error structures. First of all, Zij is the latent utility of the essential choice model. It is a multinomial choice. And tribal behavior model is a linear model for continuous choices. And sigma J is the error covariation between essential location choice and tribal behavior models for location J. So in this case, the model structure contains a multinomial probability model. Here is a multinomial probability model, and sigma Z is the variance-covariance matrix describing the covariance between alternatives. And sigma ZY is the most important part of this model. It captures the endogeneity effects due to the essential self-selection by estimating sigma, the diagonal of this matrix. But as I said, it is very huge and complex error structures, so we need to develop some efficient algorithm for parameter estimation. So I employ the Bayesian estimation framework. So we assume the posterior distribution and prior and the likelihood. But if we estimate the parameter at the same time, by evaluating the likelihood, it is very computationally intensive. It's not efficient because the likelihood is the density function of the J+1 dimensional normal distribution. It's so huge. So instead, I don't estimate the model parameters at the same time. I estimate the parameter sequence separately. For example, if I estimate alpha, we evaluate the joint probability function. It follows that only J-dimensional normal distribution, not J+1. So in addition, when I estimate beta and sigma Z1 and sigma Y, we evaluate the joint probability function, and it follows only one dimension, not J+1. So by estimating separately, it must be more efficient than naive Bayesian estimation. So I propose the estimation algorithm tailored to the proposed model. It is an efficiency algorithm. It consists of the 5 steps and repeat the 5 steps. This algorithm can be enough efficient for the parameter estimation while allowing the complex error structure. Okay, so let me show the simulation results. In this simulation, we checked whether the proposed model can correct endogeneity bias successfully. So to do this, I generated the latent utility of the residential location choice model and probability outcomes. Why? For 300 samples. So that it is the overall model structures, so the latent utility for the 6-dimensional normal distribution. And I said sigma 1 is fixed to 0, but sigma 2 is 0.3 and sigma 3 is minus 0.3. By doing so, y1 is missing randomly because sigma 1 is 0, but y2 and y3 are missing not randomly because sigma 2 and sigma 3 are not 0. By doing so, endogeneity bias occurs in estimating model parameters of probability behavior y2 and y3. This is the estimated results, and this is the true parameters I used when I generated the simulation data. And it is the estimated result when sigma is clearly estimated, and it is the result when sigma is fixed to 0. And as you can see, this is the table of the ATE, average treatment effect. It means the causal effect. So it is the true ATE using the true parameter. And this is the ATE when sigma is clearly estimated, and this is the result when sigma is fixed to 0. And yeah, it is obviously that when sigma is clearly estimated, it's very close to the true values. But when sigma is fixed, it can be far from the true ATE. So it is shown that by estimating sigma, we successfully corrected the endogeneity bias.
You go back to the so the next one, the one with the result. I think I said it wrong. I mean the one with the simulation result. So I'm not entirely sure, but it seems that the only parameter that appears to be biased is beta to 0. Is that right?
Yes, it is a constant.
It is a constant. Yeah. What's do you have an intuition about why it's only that parameter, the one that's getting biased or the other one?
Thank you.
Maybe the 3.0 is also, maybe there's something to forget. Although I can't really tell and miss like the posterior probability intervals. You see, but it seems that maybe 2 parameters are biased.
Yes. Yes, this is because I assume the independence between the error terms and exploited variables. But yes, actually in reality, these exploited variables and error terms are created. So when I use in reality the real data, other parameters can be biased. But in this simulation, we assume that independence between exploited variables and error terms. That's why only the parameters of the constant parameters is biased.
The bias is actually in the opposite way. So it's probably consistent with the signs of the sigma.
Yes, yes. So that's why this parameter is greater the true parameters. Yes. And it is lower than the true parameters. Yes, because it's the opposite. I assume 0.2 and minus 2. So it's a naive simulation. Yeah, that's why. Maybe I should simulate endogeneity by omitting variables. Yes. But in this case, I just set sigma to dynamic endogeneity because I'd like to check the differences between two parameters. Okay, let me go on the case study. Okay, in this case study, the aim of this case study is to examine the causal effect of relocation to around the train station on individual car ownership probability in Kumamoto City, Japan. So I assume treatment and control groups at the residential location within 1,500 meters from the nearest train station and between 1,500 to 1,300 and over the 1,300. Yes. In this case, this residential location choice assume multinomial endogenous switching. And in this case, we assume the binary car ownership. So we assume the latent utility and y1 if the latent utility is greater than 0, otherwise it's 0. And if the error term between this and this are correlated, the probability behavior outcomes, the binary ownership results are missing, not randomly.
So, the one thing that I don't understand, if we have these two control groups, the treatment effect is calculated using one, using the other, using the average of the two, like how do you combine the difference between treatment of control 1 and treatment of control 2? Maybe
Yes.
explain that again.
Yes. Yes, the causal effect is defined the differences between treatment group and control group 1.
But if you have, okay, so only control group 1?
No, also treatment group and control group 2.
So you have two estimates?
Yes, yes.
Then the other, do you combine them or just
Separated.
okay?
So it is the basic analysis of this data, and we use the 2012 household travel survey of city. And yeah, this for this over the 70 years old. And people living within 1,500 meters from the nearest train stations, only about 60% own a car, and otherwise they don't. But over the 1,300 meters from the nearest stations, 70% of the respondents own their car. So this is a naive aggregation, but it shows the 10.5 point differences between people living within 1,500 meters and over 1,300 meters from the nearest train station. So I'd like to check whether the differences due to the access distance or not, or it is due to endogeneity issues. And this is the result. And it shows the expected ownership probability. And the orange is the results when sigma is clearly estimated. In other words, the results dealing with non-randomly missing, so addressing endogeneity. And blue one is when sigma is fixed to 0. It means ignore the endogeneity issue. So as you can see, when we focus on the blue results, it shows access distance it can decrease the ownership probability. But focusing on the orange results, there's no difference between the three groups. So 80 is there's less 80 compared to the results when sigma is fixed to 0. So it implies that assuming the random assignment to essential location can lead to the false conclusion. So in this case study, the relocation from the over 300 meters to within 1500 meters from the nearest train station can reduce their ownership levels. And I want to discuss why such heterogeneity bias occurs. Assuming people with attitudes toward using public transportations, if they tend to live in the nearest train stations, yes, they use public transport, but they want to public transportation, not own a car. So that's why when sigma is fixed, the results is lower than the results when sigma is estimated. And it is the same when analyzing people within the distances. But focusing on people living over 300 meters from the nearest train stations, the blue result is greater than yellow result. So if people with attitude toward driving a car, living in suburban areas, yeah, such a result is shown. So the advantage of this approach is to check whether heterogeneity bias occurs, distribution occurs in each decision location, not just correcting the bias. And I would say it is due to the additional variables and unobserved additional variables. So for conclusion, we propose extended sample selection models, which assume multiple treatment groups. And it can identify a causal effect of interventions on traveler behavior in the living causal model framework. It means it assumes treatment and control groups. And the proposed sample selection models describe the non-random listing data mechanism of traveler behavior outcomes, because it assumes multinomial endogenous switching. And I applied this proposed model to Kumamoto City data, and it revealed that location around the train station couldn't reduce their ownership levels. But when analyzed data naively, it leads to the false conclusion. So we need to check whether heterogeneity issue is addressed or not in actual data using such a model, proposed model. So thank you for your attention. So do you have a comment? Thank you very much. Thank you.
So yeah, so Karina,
Yes.
hay preguntas en YouTube, no sé si hay gente en YouTube, ¿cuántas hay? Pero, but let's see, do you have any questions from the room? If you want to make it in Spanish, feel free, and I can do my best. No, yeah.
No hay preguntas en YouTube.
Yeah, gracias. I have a question. I mean, in the line of what Andres, Andres is professor from industrial engineering here at the university. Yeah. So I mean, the methodological extension that you propose is to use this let's not call it multiple treatment, but multiple controls on this. So I'm confused about I mean, in the example that you showed there, the second ring is also be seen as a control if you want to get closer to the station than the other one. So why you control? Why you only call the treatment the one that is closer and not the other ones? Would not that cause some issue?
Yes. I would like to analyze the effect of relocation from the power from rail station to around the train station. If the causal effect is big, relocation from the power from rail station to the nearest trains around the train station, like a TOD policies can affect, can reduce the causal levels of individuals. So I wanted to check whether it's effective or not. So I put it on the
Okay. And you said, so let me, and then, so this is the, I mean, from the real data. So if I understood you at the end, so if the effect is weaker, you can claim that it is due to the, or stronger if you want, as you get farther away.
from this analysis.
Yeah.
Yes. Not using this data.
No.
Yeah.
But,
I'm seeking more applications. For example, I'm analyzing the data, the 2017 National Health Survey, and the probability outcome is BMT, Human Virus Survey, and I assume urban second city and suburban city. So I assume living in urban cities as a treatment, and others as a control groups. So I'm analyzing this data.
yeah, I don't know. Yeah. So do you have any comment? I have another question. So, and which variables did you use for the the switching model? Which are the let's see the W's? I don't know what do you call it. What's the specification of the model? Which are the W's and which are the X's?
W.
Yeah, for the choice model. Yeah.
Yes, it is an explanatory variable.
Yeah. Which ones? Which were the variables that you use? Yeah.
Includes social demographic variables like gender, age, and yearly incomes, and their jobs and household members.
The job, the number of people working.
The number of household members.
Working, yeah.
And the expected variable in travel behavior analysis has almost the same variable.
But you need some to be different.
Yes.
Yeah, here you have a question.
I have one question about the case study. Do you know how much is the average distance between rail stations?
Yes. About, actually, I'm not sure, but 1,500 meters from the train station is the average. The most, so this is the most nearest to the average. I remember, but I'm not sure the exact average of this time.
But between one station and another.
From the nearest train station. Or the nearest station, the distance. So only the nearest.
So, but the other one, because the ring that you defined was 3 kilometers, so, and the next train station was closer. I mean, to I mean, within that ring, you may have another train station. That's the, I guess that, yeah, that's the,
yes.
it may be the case.
Yes. In this case, we consider the distance between home and only the nearest
10 years.
Yeah. But yes, some people, yes, living around the station, around the some station. So yeah, I should consider such a multiple autonomy station.
Okay, so another comment on question?
Maybe Angelo already asked this, but is there one variable that appears in X but not in W, or are the same variables appearing in X and W? Is Xi the same as Wi, or are they different vectors?
Yeah, maybe we can.
Sorry. Explanatory variables in all travel behavior models are the same.
So X is identical to W?
No, not identical. Because the W is explanatory variable in a essential location case.
Okay, so what are the variables in X? What are the variables in W?
Yes. I consider some job variables, explanatory variables about their jobs in this essential location choice model.
That would be for W or for X? For W.
Oh, W, yes.
So you consider what? Like the job, like the occupation of the
Yes, occupation and household members.
Okay, household size. Okay.
Yes.
And those are not included in the Y in the X.
Yes, because these variables are not statistically significant in travel behavior model. That's why I excluded some models to the other.
So for the X, what did you use? Did you use, I don't know, like income or?
Yes, income and other social demographic variables, they are individual attributes. And whether they have a household member who have own a car, yeah, something like that. But the household attributes are included. But I checked which variables are significant or insignificant. And insignificant variables are excluded. And as a result, W and X are not identical variables.
Okay, so any other comment or question? Thank you. Okay, so if we don't have no questions, so yeah, we'll finish here. Thank you very much, Hajime, for your presentation, and yeah, we're happy we're glad to have you here. Thank you everybody for coming to the.
Thank you very much.